Hey, this is Mr. Aiden, and this is Chemistry Honors video for Bronsted-Lowry acids and bases. Our last video was Arrhenius acids and bases, but this one is we're talking about specifically Bronsted-Lowry acids and bases. So, how do Bronsted-Lowry acid bases differ from Arrhenius? Well, Bronsted-Lowry acids and bases are dealing with weak acids and bases. This is actually what Mr. Dale really looks like. He's bald, he's skinny, he's weak in real life. He's not like the Arrhenius or the strong acids and bases. It's the weak acids and bases. So what do we know about weak acids and bases? They don't dissociate 100% like strong ones. They dissociate 5% or less for the most part, which means if they don't break up into ions, if they don't dissociate very much, well, that's going to be a weak electrolyte. They're not going to be very poor conductors of electricity. So we're not going to write H+, we're not going to write OH-. They are mostly molecules in solution. 95% of them are molecules. There's only about 5% that are positives and negatives, which means when we write Bronsted-Lowry acid bases, we need to write them in their full molecular form. Their full molecular form. And so, what do we know about Bronsted-Lowry acids? These are ones like HF, hydrofluoric acid, or vinegar or acetic acid, that's HC2H3O2 or CH3COH. And what do we know about Bronsted-Lowry acids? They are proton donors. They have H+, so they give away H+, which means Bronsted-Lowry bases are proton acceptors. They accept the H+. And this is something like ammonia or CH3NH2. These Bronsted-Lowry bases accept the protons, whereas the acids give away the protons. So the big thing we want to take a look at is what we call our Bronsted-Lowry acid and base reactions. And so let's first take a look at our Bronsted-Lowry acid reactions. And here we have HA. Now HA could stand for anything. It could stand for HF. It could stand for HC2H2O2. That A stands for a bunch of different things. So it's kind of like a variable, which means this is our acid. Our HA is our acid, which means water here is acting like a base. Water will be acting like a base, which means what do we know about Bronsted-Lowry acids? They give away H+, which means if the HA gives away H+, it becomes A-, which we call our conjugate base. Okay? It no longer has the H+. And the water gained the H+, which means it becomes hydronium or H3O+, which we call our conjugate acid. And this H3O+ is what we would be able to do our pH. We're not allowed to do our pH equations right away with Bronsted-Lowry acids or bases because we don't have 100% of H+. We only have a very, very small percentage of H+. So that's a Bronsted-Lowry acid reaction. Let's take a look at a Bronsted-Lowry base reaction. This B variable is going to be our base. It could be anything. It could be something like NH3. It could be some different kind of weak base, which means the water here is acting like an acid. And what do we know about Bronsted-Lowry acids and bases? Acids give away H+, the bases accept the H+, which means the B, or the base, would gain the H+, and become BH+, which we call our conjugate acid. Our conjugate acid for NH3, that would end up becoming NH4+, which is called our conjugate acid-base pair. The water, when it gives away H+, ends up becoming OH-, which is hydroxide, or what we would call our conjugate base. And again, this is what you would do with your pH equation right here. And so this is our Bronsted-Lowry acid-base reactions, and we have what's called conjugate acid-base pairs. How do we know what our conjugate acid-base pairs are? Something like HA, his conjugate acid-base pair would be the A-. Something like the B for the base would be the BH+. Those are our conjugate acid-base pairs. Well, hopefully that helped. That was a quick tutorial of Bronsted-Lowry acids and bases. Make sure you go to MrAiden.com, finish out your self-assessment on Bronsted-Lowry acids and bases, and I'll catch you on the flip side. See you later.